In this video, we're going to learn a different type of substitution where we actually rewrite our variable in terms of trig functions of another variable. It's called trigonometric substitution, and it's where we actually introduce trigonometry into a problem that doesn't look like it has trigonometry in it, but it allows us to actually calculate the integrals. So in order to do trigonometric substitution, you need to be very familiar with the Pythagorean Theorem and your right triangle trigonometry. So just a reminder for us, when we have a right triangle that has legs A, B, and a hypotenuse C, the Pythagorean theorem tells us a squared plus b squared equals c squared. And if I chose to solve this equation for one of my variables, I would have a equals the square root of c squared minus b squared, or I would have b equals the square root of c squared minus a squared, or I have c equals the square root of a squared plus b squared. So in our integrals that we're going to be doing, we're going to have terms that look similar to these right-hand sides here, where we have a square root with something squared plus or minus something squared. And we're going to use this information from the Pythagorean theorem to rewrite our integral using a right triangle in trigonometry. Remember, for example, if I put an angle theta over here, then from trigonometry, we know that sine of theta is my opposite over the hypotenuse, so a over c. Cosine of theta would be adjacent over hypotenuse, b over c. And just squeezing it in over here, my tangent of theta would be my opposite over adjacent, a over b. So we're going to need all of that sort of information when we're going to be doing these new types of problems. So the best way to learn trig substitution is, quite frankly, just to do it. A lot of books suggest that you memorize these different substitutions. When you see something in this form, then your substitution is going to be x equals sine of theta or something like that. I suggest you do not memorize those things. I think it's much easier to understand what's going on if you just take your integral and draw a triangle from it every single time and set it up using our Pythagorean theorem and our right triangle trig. So let's just start right away with an example and see what exactly I'm talking about. So our first example, we're going to do an integral of a square root of 9 minus x squared over x squared dx. And now the very big clue that this would be a great problem to do this sort of trig substitution is that square root of 9 minus x squared in the top. That looks very similar to some of the things I got when I was solving my Pythagorean theorem for one of my sides. So let's just draw a triangle and see if we can find a triangle that matches our information. So remember, when we had our Pythagorean theorem, the a squared plus b squared equals c squared, a and b are the sides, c is the hypotenuse. I want something that has a minus sign under the square root. So that would be if I solve my triangle like this for one of the sides. It doesn't matter which side it is, I just know that since I have a minus sign underneath that square root, that means that I've solved for one of my sides. Now, underneath this square root, I have a c squared first, and that was my hypotenuse. And the b squared came from my other leg. So looking at my particular problem, I have, let me just write this down, I have the square root of 9 minus x squared. So that means this 9 corresponds to the hypotenuse squared. The x squared corresponds to one of my legs squared. And then the entire square root is equal to one of my legs as well. So let me just put in all of our information. Since my hypotenuse is 3 squared, I know, well, my hypotenuse squared is 3 squared. I know my hypotenuse is 3. I know one of my legs is going to be x, and my other leg is going to be the square root of 9 minus x squared. So take a look at the triangle, make sure it satisfies the Pythagorean theorem, which it should, that's how we set it up. But if you take a look at it, my x squared plus this square root squared would equal 9, and that equals 3 squared. So it does satisfy my Pythagorean theorem. So this is the triangle we're going to use when setting up a substitution to solve this integral. So it doesn't matter which leg you put things on or where you put your theta. I tend to put my theta in the lower corner like that, and I tend to put the square root term, if it's a leg, I tend to put it on the bottom because there's more room to write horizontally. It does not matter either way, you'll get the equivalent answer at the end. You'll just be using different trig functions if you set it up with your legs on the other sides or you're using a different angle for your theta. So now using my right triangle trig, I want to find an expression for x, an expression for dx, and I want to find what the square root is equal to. So first thing I notice is if I look at this theta here, the opposite side is x and my hypotenuse is 3. So I know that sine of theta is equal to x over 3. At that point, I automatically go ahead and also solve for theta just in case I need it. My theta will be the inverse sine of x over 3. Sometimes we need that in the problems and sometimes we don't, but it doesn't take long to just write it down right away. So I have sine of theta is x over 3. If I solve that for x, I get 3 times sine of theta is equal to x. I'm going to use that in my substitution. I also need to know what dx is. Well, that's just the derivative. The derivative of 3 sine theta is 3 cosine theta d theta. And now if I look at what I have in my integral, technically we can just go ahead and do our substitution now. I could plug in 3 sine theta for all of my x's, and I could plug in 3 cosine theta d theta for dx. It'd be kind of complicated under that square root, but you could use your trig identities to simplify it. Or you can do what I think is easier and just figure out what the square root is equal to using our right triangle trig. If I look at this triangle and I look at the adjacent edge and the hypotenuse, I know that cosine of theta is equal to the square root of 9 minus x squared over 3. And that means solving that, I have 3 times the cosine of theta is equal to my square root of 9 minus x squared. So I found all of that information just by writing down a triangle and seeing what I have. Now we need to rewrite our integral using this information. Erasing most of that, I'm going to keep these here because those are the ones I'm really using for the most part. So my original integral was the integral of the square root of 9 minus x squared over x squared dx. And now I'm going to rewrite it using this triangle. That entire square root was equal to 3 cosine theta. My x squared would be 3 sine of theta squared. And I got that just by looking at what x is equal to. And then my dx is 3 cosine theta d theta. And that looks terrible, and I'll fully admit that, but it will simplify and make our lives much easier. So let's just simplify as much as we can. What I have then, I'm going to just think of this as over 1, multiply the tops together, so I get 9 cosine squared of theta. And in the bottom, I have 3 sine of theta times 3 sine of theta. That's 9 sine squared of theta. Okay, d theta. Now, what do we do from there? Well, the 9's cancel out, so that's good. And then I know that cosine squared over sine squared is a cotangent squared of theta. And now what we've done is we've magically turned this problem into one that's like the problems we did in the last section. I can now solve this just using a trig identity and integrating. So cotangent squared is equal to a cosecant squared minus 1, just using trig identities. And now this is something I can do the antiderivative of. The antiderivative of a cosecant squared is a negative cotangent. And then the antiderivative of the minus 1 would be a minus theta. And don't forget your constant. And now are we finished at this point? Unfortunately, no. At this point, you got most of it, but the problem is the original problem had x's in it, and this has thetas. So we need to get it all back in terms of x. Now I had what theta was equal to in my list of things, but I did not have a cotangent written down. So let me just remind us what our triangle looked like. Our triangle had a 3 over here, an x, and a square root of 9 minus x squared. The cotangent of theta is equal to, instead of it being opposite over adjacent, it's adjacent over opposite. So I have my adjacent side is square root of 9 minus x squared. My opposite side is x, and that is my negative cotangent of theta. Now my theta, we had that in our list of things before. That was the inverse sine of x over 3. And then add your constant, and that is the answer to the problem. So we took a problem that we would have been unable to integrate before. We couldn't just use substitution on it. Integration by parts would go terribly. But we're able to rewrite it using a triangle and trigonometry and make it into something we can integrate, not too terrible. Let's do another example. These just take a lot of practice to get the hang of. So another example. Let's find an integral of 1 over x squared times the square root of x squared plus 4 with respect to x. And again, the big clue that we want to use a trigonometric substitution is this square root term. I have a square root of a sum of squares. So I know I can write a triangle that satisfies the Pythagorean theorem and matches the info in this integral. So this time we have a plus underneath the square root. And that means that the square root is actually equal to the hypotenuse. And the x and a 2 are my legs. And again, it doesn't matter what sides you put them on. I'm just going to put the x on the side and the 2 on the bottom. Now take a look, make sure this satisfies your Pythagorean theorem. X squared plus 2 squared is equal to the square root of x squared plus 4 squared. It does work. So you just have to remember, when you have a plus underneath the root, the square root goes on the hypotenuse, and the other 2 pieces are the legs. If there's a minus under the square root, then the guy in front of the minus is the hypotenuse, the other guy is a leg, and the square root is a leg. And then you're all set. All right, so now looking at my triangle, we need to figure out what x is, what dx is, and what the square root is. So looking at this triangle, I see that if I use a tangent, I will have tangent of theta is x over 2. I want to use tangent because that relates my theta to my x in the simplest way possible. I'm using just the side that has an x and just the side that has a constant and nothing more complicated. Now using this, I know that theta is also equal to the inverse tangent of x over 2, just in case we need it. Taking my tangent of theta equals x over 2, I can solve for x. 2 times the tangent of theta is equal to x. So now I know what x is, I can plug that in for the x squared, and we can find dx by taking the derivative. The derivative of 2 tangent theta is 2 secant squared of theta d theta. So now I have the x, I have the dx. Let's just figure out what the square root is and we're good to go. So I want to relate the square root to theta. So I should use this side on the bottom as well because that side is just a number, so it's the easiest to work with. So that would be the adjacent side and a hypotenuse. Cosine of theta is equal to the adjacent over the hypotenuse. So if I multiply both sides by the square root of x squared plus 4, and then divide by cosine theta, I get the square root is equal to 2 divided by cosine of theta, which is the same thing as 2 secant of theta. And now we're ready to plug our stuff in. So let me rewrite my integral. I'll erase the triangle for now and just rewrite this integral using all of this information. My x squared would be 2 tangent of theta squared. And then I have a square root, so that's 2 secant theta. And then I just have to plug in my dx. So there's my dx. dx was 2 secant squared of theta d theta. And now we're ready to simplify as much as we possibly can. So first thing I notice is these 2's cancel out and one of my secants cancel out. And I can square this 2 tangent of theta. So I will get, I have a secant left on the top. On the bottom, I'm going to have 4 tangent squared of theta. And I have a d theta. And now what do we do from there? Well, I'd probably change this into sines and cosines and hope that it gets a little easier to work with. So knowing what sines and cosines are for these different trig functions, secant is equal to 1 over cosine. 4 tangent squared theta would be 4 sine squared theta over cosine squared theta. And so when I end up flipping and multiplying and simplifying this crazy fraction, we'll get something much easier to integrate. I'm going to have a cosine on the top and 4 sine squared theta on the bottom. And I'm going to go ahead and pull that 1/4 outside because I know that a lot of you prefer it that way. And there we go. Now we're finally ready to get this integrated. But it's not quite as nice as the last problem. I can't just integrate it directly. We have to use a regular u substitution to finish this problem up. If I choose u equals sine of theta, then du will be cosine theta d theta, and it will take care of that issue for us. So let's set up a regular u substitution on top of our trig substitution. Let u equal sine of theta. So du would be cosine of theta d theta. And that means d theta is du divided by cosine of theta. So my integral is now equal to, we would have had a cosine theta over u squared and a du over cosine theta. So the cosines cancel out. And I just have a 1 over u squared. Well, that's the same thing as a u to the negative 2 power. So now I'm ready to integrate this just using a power rule. Using the power rule, we're going to end up with a u to the negative 1 and divide by a negative 1. So that makes it negative 1/4 u to the negative 1 plus our constant. And are we finished at that point? No, we're not. First, I would rewrite the u to the negative 1 in the denominator. Then we can plug our u back in, and then we'll see where we're at from there. So moving that u to the denominator, I get negative 1/4u plus c. U is equal to sine of theta. So let me plug that back in. And we get negative 1/4 sine of theta plus c. And now, am I finished at this point? We're still not finished at this point because we have our answer in terms of theta. And we need our answer in terms of x. So what do we do from there? You look back at your triangle. So let me redraw my triangle for us. Our triangle had square root of x squared plus 4 as the hypotenuse. It had an x on the side and a 2 on the bottom. So what is sine of theta? Sine of theta is equal to the opposite over the hypotenuse. So I have x over square root of x squared plus 4. So now I can take this and plug it in for my sine of theta. Let me just put that up on the top. So we have a negative 1/4 times x over square root of x squared plus 4 plus c. And of course, we can write that better by flipping that sign upside down since we're dividing by it. And we get negative square root of x squared plus 4 on the top and 4x on the bottom plus c. And there we go. So that problem had a lot involved with it. We had to first find our triangle, do some trig substitution, play around with sines and cosines, and then we had to do a regular u substitution on top of it. And then make sure we back substitute all the way back so that we're back in terms of x and not theta or u. All right. Let's do another one. Right about now, I would have students wondering if we have to do a definite integral ever with trig sub. And the answer to that is, of course you do. So let's just do an example with definite integrals. And we'll see how that goes. So let's do the integral from 0 to 3 square root of 3 over 2 of x squared over 4x squared plus 9 to the 3/2 power dx. Now, at first glance, you might be a little confused about this one because it does not look like the other problems we just did. I don't explicitly have a square root written in this problem, but it's there. I have a 3/2 power. That means I have a square root and it's to the 3rd power. So I'm going to rewrite this first so it looks like we're a little more used to when trying to set up our triangle. I have an x squared on top. I have a square root of 4x squared plus 9, and that square root is to the 3rd power dx. And now we're ready to set up our triangle for our trig substitution. So let me set up this triangle. I have a plus underneath the root, so that means this 4x squared and that 9 correspond to my sides squared. And the whole square root is my hypotenuse. So we put the square root of 4x squared plus 9 as my hypotenuse. And my sides of the triangle are going to be 2x and 3. Remember, underneath that square root are the different sides squared. So you have to take the square root before you label your triangle. So there's my triangle. Now let's see what we get from this triangle. First, let's try to figure out what x is. Well, I would use a tangent on this one because my tangent would involve this 2x and the 3, and those are the easiest ones to work with to find my x. So tangent of theta is equal to the opposite over the adjacent. Go ahead and quickly write down what the theta is equal to, just in case we need it. We know in our first example in the video, we needed that theta. The second example, we did not, so it doesn't hurt to just write it down real quick. Now, solving my first equation for x, I get 3 over 2 tangent of theta is equal to x. And now I can find dx by taking the derivative and get 3 over 2 secant squared theta d theta. And now we're almost set, but we need to find what that square root is as well, because we want to replace that in our integral. What is the square root equal to? And here, let me just put that over here. I'm going to try to save some space, so maybe we can put the integral at the bottom. Using this adjacent side and the hypotenuse, I get that cosine of theta is equal to 3 over the square root. And that means that my square root of 4x squared plus 9 would be equal to 3 divided by cosine of theta, which is 3 secant of theta. And now we're almost set. At that point, we also need to change our bounds. We have definite integral on this problem, so let's change our bounds of integration. Our first bound was x equals 0, I believe. Let me double check before I write that down. Yes. When x is equal to 0, what is theta going to be equal to? Theta would be the tangent inverse of 2 times 0 over 3, which is tangent inverse of 0. That is 0. I hope you know your unit circle really well, so you can also do the inverse trig functions when changing your bounds. And for those of you that don't like changing your bounds, you're still going to have to know your inverse trig functions to be able to do the problem, because you either have to do it when changing the bounds, or at the end when you're plugging the original bounds back in anyway. My other bound was when x was equal to it was 3 times the square root of 3 over 2, which looks pretty terrible. But this problem was very well designed because I have 2/3 times x inside my tangent. 2/3 of this is just tangent inverse of the square root of 3, and that happens to be pi over 3 using my unit circle. So unfortunately, I don't have room to write my integral at the bottom, but we have everything that we need written down. Let's see, I think I can erase these 2 lines up on the top so I can write down the original integral, and we still have everything we need on the board for writing the problem. So my original integral, remember, was an integral from 0 to 3 root 3 over 2 of, it's on my other page, it was x to the 3rd over our square root of 4x squared plus 9 to the 3rd power dx. So now, rewriting with my substitution, my new bounds are 0 to pi over 3. On the top, I have well, it should be x squared, not x to the third. I don't know why I wrote an x to the third there. Our original problem had an x squared. So x squared, x is 3/2 tangent theta. So I'm going to have 3/2 tangent of theta squared. And my denominator is the square root to the third. So that's 3 secant of theta to the third. And then my dx is 3/2 secant squared theta d theta. All right, let's see what happens when we simplify this. So simplifying this integral, on the top we're going to have 9/4 tangent squared of theta. On the bottom I have 27 secant to the third, and then times 3/2 secant squared d theta. And simplify as much as we can. I can cancel out some of the secants, and I can play with the way that the numbers are written here. The 9 and the 3 on the top are going to cancel the 27 in the bottom here. And I end up just having a 1/4 and a 1/2, which is 1/8. Integral from 0 to pi/3, tangent squared of theta over secant theta d theta. And I would do what we did in the last problem and change this into sines and cosines most likely. Or I could use a trig identity if I wanted to. You know what? Let's do that. Let's use a trig identity. So my tangent squared of theta, if I rewrite that in terms of secant squareds, what do we get? So I have 1/8 integral from 0 to pi/3. And, you know, I've actually changed my mind. I'm going to use sines and cosines like I originally did, because that was my first gut instinct. You probably could do this using the trig identity and it would be just fine, but a lot of times it's good to trust your instinct. So I'm going to do this with sines and cosines like I originally said. So tangent squared is sine squared over cosine squared. And the secant on the bottom is the same thing as multiplying by a cosine. Because secant is dividing by a 1/cosine, so it flips. So changing it to sines and cosines, I can then cancel some stuff out. I get sine squared theta on top, cosine of theta on the bottom, d theta. Now, what do we do from there? Well, you might think you're kind of stuck, but we're not, because this is actually something we know the antiderivative of. You might not realize that right away. Well, actually, not quite, but we can get pretty close. Let's see. So this is equal to, I have sine of theta over cosine theta times a sine theta d theta. So I have a tangent theta and a sine. Well, no, we're going to want a trig identity at this point. I was really hoping we could avoid the trig identity because I know a lot of you guys don't like them, but we're stuck. We have to use a trig identity, but at least changing it to sines and cosines first allows us to use the sine squared plus cosine squared as one identity rather than remembering the one with tangents and secants. So sine squared of theta is 1 minus cosine squared of theta. And now I can split this guy into two fractions. So I get 1/8 integral from 0 to pi/3 of 1 over cosine theta minus cosine squared theta over cosine theta d theta. And now we're good to go, because 1 over cosine theta is the same thing as secant of theta, and cosine squared over cosine is just cosine. And this is something I can take the antiderivative of. If you remember from the last video, we know what the antiderivative of secant is. It is natural log absolute value of secant theta plus tangent theta. And then I have my minus cosine of theta. I have to do the antiderivative of that to get a minus sine of theta. And then we're ready to plug in our bounds. All right, so now we just have to plug in our bounds of integration. So we get 1/8 times the natural log absolute value of secant of pi over 3 plus tangent of pi over 3 minus sine of pi over 3 minus what I get when I plug in the 0. So 1/8 natural log absolute value of secant of 0 plus tangent of 0 minus sine of 0. And now it's just all a matter of how well do you know your unit circle. So pi over 3 is talking about this angle up here. So this was the point 1, 0. This is 0, 1. So I know this point here, the x value is going to be a 1 over 2, and the y value is going to be square root of 3 over 2. So cosine of pi over 3 is 1/2, and sine of pi over 3 is square root of 3 over 2. We're going to use that to simplify this. So natural log absolute value. Secant is 1 over cosine. Cosine is going to be 1/2. 1 over that would make it 2. Tangent of pi over 3 would be my sine over my cosine. Square root of 3 over 2 over 1/2 gets me square root of 3. Then my sine of pi over 3, again, is square root 3 over 2. And now let's take a look at what happens with all the zeros. Here's where 0 is on my unit circle. Sine of 0 is 0. Cosine of 0 is 1. So when I plug in the 0, secant of 0 would be 1 over that 1, just 1. Tangent of 0 would be 0 over 1, which is 0. Sine of 0 is 0. And take a look at this last bit here, natural log of 1 plus 0. That's natural log of 1, which is 0. So this whole last term is 0. That means my final answer ends up being 1/8 times natural log absolute value 2 plus the square root of 3 minus square root of 3 over 2. And there we had a definite integral using trig sub. Now notice that when I was doing a definite integral, I did not plug all of my thetas back into x's before I evaluated. And that was because I changed my bounds of integration to be theta values. I feel like that saves a lot of time rather than converting it all back to x's and then plugging in the x values, but it is a matter of personal preference. So those are the 3 examples I have worked out for you today. Trig substitution does get easier the more examples you do with it. I really highly suggest you draw a triangle every single time to make sure you get it set up properly. If you have any questions, feel free to drop them below, Or if you're a current student, you can also ask in office hours or email or in class. And I will see you guys next time.